In 7.4, we're integrating rational functions by partial fractions. Most of the work will be algebraic, decomposing the fractions, and then a lot of the time we'll get simple u-subs or ln's or arctans. There can still be some weird stuff, but for the most part, they'll be nice. So video could be long, lots of algebra, lots of taking you through all the different possibilities you can see for decomposition if you haven't seen it in a while. So let's get to it. Note here, if we add the fractions 1 over x minus 3 plus negative 1 over x minus 2, we get 1 over the quantity x squared minus 5x plus 6, right? We get the common denominator. Simplify the numerator. Decomposing fractions will take us back in the other direction. So why do we want to do that? Here's your motivation. You can do 1a the same way we did 7.3. It doesn't have that square root in the denominator that screams trig sub, but it is still a quadratic expression down there that we can complete the square on and get into a trig sub form. So pause and try or follow along, but our start will be to complete the square. All right, so to complete the square, we've got 2b equals negative 5, right? The coefficient of the linear term there, which means b is negative 5 halves, and b squared is 25 fourths. So we can rewrite our integral as a 1 over the quantity x squared minus 5x plus 25 fourths and minus 25 fourths to make our perfect square trinomial and stay balanced, and then the plus 6. And then rewrite that in our factored form. A 1 over x plus b, our b is negative 5 halves, so x minus 5 halves, quantity squared. Negative 25 fourths plus 6, which is 24 fourths, leaves us with a negative 1 fourth. And then we're in that variable expression squared minus constant, a 1 half squared. So we get our trig sub with secant. And so that whole variable piece, x minus 5 halves, is equal to a 1 half secant theta, right? 1 half is our a. And then two things from there. We can do dx first. Take our derivative, left side is just 1, so dx equals a 1 half secant theta tangent theta. And just to make our sub slightly easier, x minus 5 halves quantity squared is a 1/4 secant squared theta. So we can continue over there with our trig sub and rewrite our integral as, let's put a 1 half outside here, secant theta tan theta. I didn't write it over there, but we can squeeze in our d theta over our 1/4 secant squared theta minus 1/4. If I factor out the 1/4 in the denominator, I've got a 1 half divided by 1/4, which would give me a 2, right? 1 half times 4. And then I've got a secant theta, tan theta, d theta in my numerator still, over my secant squared theta minus 1, which again, the reason for the trig sub is to get that down to that single term. So our secant squared theta minus 1, we can rewrite it as tan squared theta. And then we'll get rid of one of those tans. So we can rewrite this as 2 times our quantity. We've got secant theta over tan theta d theta, and then rewrite some more because lots of trig. Secant is 1 over cosine theta, and dividing by tangent would be times cotangent, which would be cosine theta over sine theta d theta. And our last line here are fully simplified after all our trig stuff. 1 over sine we can write as cosecant theta d theta. All right, and if you don't remember how to integrate cosecant, or if you haven't done it in a while, or we haven't done it together yet, it's similar to secant, where we've got to multiply by the correct something. The something we're going to multiply in this case by is a cosecant theta minus cotangent theta. And we've got to do that in the numerator and denominator to multiply by 1 and again, keep everything balanced. And so we can rewrite this as 2 times the quantity cosecant squared theta minus cosecant theta cotangent theta d theta. over cosecant theta minus cotangent theta. All right, and so that's going to be a simple-ish u sub. Our u is going to be that whole denominator we brought in, cosecant theta minus cotangent theta. Our du then, cosecant derivative minus cosecant theta, cotangent theta. And negative cotangent would go to a positive cosecant squared theta, d theta. Luckily, that's what we have in our numerator. So we get a 2 times the quantity, 1 over u du. All right, and then if we integrate, we get a 2 times natural log of u, which is, do we need a plus c? Yeah, we need a plus c, which is 2 times natural log of cosecant theta minus cotangent theta plus c. And then to finish our trig sub, we've got to go back to x. So we'll put our triangle over here on the left and do some more algebra maybe. Let's see that original sub. So the x minus 5/2 equals 1/2 secant theta. If we multiply both sides by 2, we get a 2x minus 5 equals secant theta. And we can use that to draw out our triangle. All right, secant would be hypotenuse over adjacent, so 2x minus 5 up here over a 1. And then our other side will be kind of ugly, but let's see. Square root of that whole 2x minus 5, quantity squared, minus 1, right? 1 squared being the leg there. And just for fun, and so we don't have to do it later, that 2x minus 5, quantity squared, minus 1, is going to multiply out to a 4x squared minus 20x plus 25, but the 25 minus 1 will give us a plus 24. All right, so keep going. We want to get everything back to x. We've got a 2 times natural log times, or in our absolute value here, cosecant theta would be hypotenuse, 2x minus 5, over opposite side, so the square root of that 4x squared minus 20x plus 24. And then minus cotangent would be adjacent 1 over opposite, so that same square root. 4x squared minus 20x plus 24 plus c. And if you were doing this on a test in class 7.3, whatever, you can kind of stop there, right? We got everything back to x, but we're going to keep going for a minute and do some more algebra just to show you that it is equivalent to what we'll get with b here in a sec. So we've got 2 times natural log over the same denominator, so we can simplify our numerator. We get a 2x minus 6, right? 2x minus 5 minus 1. And in our denominator, underneath that square root, we've got a GCF of 4, so we can take that out. We're left with an x squared minus 5x plus 6, which might look familiar. And then the plus c is still there. And if we keep simplifying, 2 times natural log, we've got a 2 times the quantity x minus 3. In the denominator, we can take that square root of 4 out as a 2. And x squared minus 5x plus 6 would factor as an x minus 2 times x minus 3. Keep the plus c. Back up. Almost done. We've got an equals, we've got a 2, which I'm going to rewrite. So we've got a natural log, the 2 out front, we can bring up inside and square everything. So the 2's down there are going to divide out, and we'll be left with an x minus 3 quantity squared over x minus 2 times x minus 3. Right, the squaring will square that x minus 3, factor those in the numerator, and get rid of the square root in the denominator. And then simplifying, natural log of one of those x minus 3's can go away, so x minus 3 over x minus 2. And using our natural log properties, we can expand it to natural log of x minus 3 minus natural log of x minus 2. And, oh god, I forgot my plus c on those ones, so plus c, plus c, plus c. All right. If you look at b now, We've got the integral of 1 over x minus 3 plus negative 1 over x minus 2. You could write out little u subs for that if you want to, but we get natural log of x minus 3 minus natural log of x minus 2 when we integrate that. So one step instead of whatever the heck I got there, 3 paragraphs of stuff, whatever you want to call that, 3 columns of work. All right, so there's your motivation, and we'll work on some partial fraction decomp now. All right, so notes. If a rational function is in improper form, meaning the degree of the numerator is greater than or equal to the degree of the denominator, we want to use long division first. That'll get us to a proper fraction or something plus a proper fraction that we can do the decomposition on. And so rules for decomposition: to decompose a rational function into partial fractions, we first factor the denominator completely. You must be able to do this nicely for the method of partial fractions to help. We put a constant in the numerator of each linear factor, repeating each factor to include every power up to its multiplicity, and we'll see that as we do it. And a linear expression we're going to put in the numerator of each quadratic factor, irreducible quadratic, repeating each factor again to include every power up to its multiplicity. So largely algebra, but we'll start by actually learning how to decompose that first one, so we can do the 1-step, maybe 2-step if you write out tiny u sub integrations there, instead of the giant work we just did with the trig sub. So first method is to substitute in convenient values for x, focusing on ones that make each factor 0. This method works really well when we have distinct linear factors, because plugging in the zeros will get rid of 1 each time and be left with usually a variable we can solve for. So to decompose into partial fractions, we first want to factor. Our factorization here is the x minus 2, x minus 3 we used eventually above. And then we just rewrite. So 1 over the x squared minus 5x plus 6 is equal to, we want a constant over each linear factor, so a over x minus 2 plus b over x minus 3. Right, no repetition, we don't have multiplicities, just means higher powers for the factors. So that's all we've got to do. And we'll work just like solving a normal rational equation. We multiply by the LCD to get rid of all the denominators. And when we do that on both sides, we're left with just a 1 equals a times the quantity x minus 3 plus b times the quantity x minus 2. And so subbing in values for x that make the factor 0, our zeros would be 2 and 3. So if I take x to equal 2, on the left side there's nowhere to plug anything in, so it's just 1. On the right side, when I plug 2 in, the b times 2 minus 2 is going to go to 0, and I'll be left with an a times 2 minus 3, right, which gives me a 1 equals minus a, or a minus 1 equals a. And then if we take x to be 3, and we sub in, left side again is just 1. For the right side, the 3 minus 3 is 0 times a now. So we get a b times 3 minus 2, or 1 equals b. And so our partial fraction decomposition, this 1 over x squared minus 5x plus 6 is equal to, what do we get? A negative 1 over x plus 2, x minus 2, plus a 1 over x minus 3, just like we saw above. I think I wrote it in the other order, but just depends on where you write your factors. So there the x minus 3 was first, and then the x minus 2, but positive 1 over x minus 3, negative 1 over x minus 2. All right, and so another method to decompose, because I don't know, some people like other ones, and some people are only taught the system of equations one, so we'll go through that too. Method 2 here, create a system of equations to equate coefficients on the left-hand side and right-hand side of the equation. So decompose into partial fractions again. I won't do the same pre-work we did with the factoring and multiplying by the LCD. We just get to the same spot. 1 equals a times the quantity x minus 3 plus b times the quantity x minus 2. And so we can simplify or rearrange the right side with an ax minus 3a plus bx minus 2b. And then further, putting all the like terms together, right? We can write the x terms as an a plus b times x, and then our constants minus 3a minus 2b. All right, so maybe we'll do this for a bigger one later so we can see a little more, but we're equating coefficients. So on the left side, we would have a 0x term plus 1. So if we equate the coefficients of the x terms, we get a 0 equals a plus b. And for the constants, we get a 1 equals minus 3a minus 2b. And so maybe system of equations, you can do a couple different ways with substitution or elimination. Might as well just multiply the first equation by 2 here. That'll make it nice. I'll write it underneath. 0 equals 2a plus 2b. And if we add these two together, I get a 1 equals minus a, or minus 1 equals a again. And then we've got 0 equals a plus b. We could plug back in anywhere, but the simplest one's the best. We get 0 equals negative 1 plus b when we sub in that a we just found, which gives us a 1 equals b. So then the same decomposition there, right? The 1 over x squared minus 5x plus 6 equals negative 1 over x minus 2 plus 1 over x minus 3. All right. For 3 here, we're decomposing one that is improper, so the numerator has the same degree as the denominator, and we've got to take care of that before we can do the partial fraction decomp. And we just want to do long division. This is a nice easy one, but they get weirder. Shouldn't be too many, but if we need to review it a little more, we can do more long division, or you can look it up. But you're always dividing first term inside by first term outside. X cubed divided by x cubed is just 1, so there's not going to be anything else we can do, no more division. Right? If it was a higher degree, we'd have to keep going, but we multiply that 1 by the outside now, so we get an x cubed plus x squared, and then subtract. Right? The goal of the long division is always to get rid of that first term, that highest degree. So the x cubed minus x cubed is 0. 4x squared minus x squared would give us a 3x squared, and then there's no other terms there, so we just get the x and the negative 1 coming down. And so we can write our initial fraction, this x cubed plus 4x squared plus x minus 1 over x cubed plus x squared, as a 1 plus, right, all that stuff that's left, 3x squared plus x minus 1 over our divisor still x cubed plus x squared, just like you'd write a remainder for normal long division. All right, and so we want to decompose that second fraction now. We'll keep the 1, but we want to break this one down. So we've got a 3x squared plus x minus 1 over, factor in that denominator, we get an x squared times x plus 1. And so we can write that as equal to a over x plus b over x squared plus c over x plus 1. All right, and so for the repeated multiplicity, x or x squared, we have to account for both, right, being there to have this LCD of x squared times x plus 1. So each gets a different constant on top. Some of them will end up being 0 sometimes. Some of them will get values for each and every value there, or each and every variable we write. But it just depends on the problem. So we're going to multiply again, both sides here, by that LCD, x squared times x plus 1. And then we'll write our remaining stuff up over here. So we get a 3x squared plus x minus 1 on the left. And on the right side, that a is going to be multiplied by an x and an x plus 1. The b is getting multiplied just by x plus 1 because it already has x squared. And when we distribute it into the c, the x plus 1's gone, so we get a cx squared. All right, and then if we sub in those zeros, if x equals 0, for the left-hand side now, those two terms that have the x go to 0, so we're left just with the minus 1. On the right-hand side, the ax term multiplied by 0 is gone, the cx squared is gone, so we get a b times 0 plus 1, or 1, which gives us negative 1 for b. And then our other 0 here is negative 1. If we sub that in, we get a 3 times negative 1 squared, which is 3. minus 1 minus 1, which is 1, equal to, on the right side, the a term is gone with the negative 1 plus 1, and the b term is gone, and we're left just with c, so c is 1. And then from here you can either go to a system of equations or just plug in some other convenient value for x. Generally 1's good if we haven't used it, so I'll plug in 1. We get a 3 plus 1 minus 1, or just a 3 this time, equals, on the right hand side, we can sub stuff in this time, a times 1. 1 plus 1 would be a 2, plus b times 2, plus c. And then we can plug in our values for b and c. So we get a 3 equals 2a, plus negative 1 times 2, so I guess a negative 2, so minus 2. And then c was 1 plus 1. Negative 2 plus 1, negative 1. And then if we add that over, 4 equals 2a, divide by 2, and we find that a is 2. So our original fraction here, the x cubed plus 4x squared plus x minus 1 over x cubed plus x squared is going to divide and then decompose into a 1 plus, a was 2, so 2 over x, plus b was negative 1 over x squared, and plus a c, which was 1 over x plus 1. All right, and so note here, there are often cases where a combination of both methods will be useful or most beneficial. I didn't end up doing that here, but we'll see it later. And 4 here then is just doing that actual integration. So we're evaluating this function, the same rational expression, x cubed plus 4x squared plus x minus 1 over the quantity x cubed plus x squared from 1 to 2. So we can rewrite our integral here with that decomposition we've got above, the 1 plus 2 over x plus negative 1 over x squared plus 1 over x plus 1 dx. Our first term, the 1, would just go to x. The 2 over x would go to a 2 times the natural log of x. The negative 1 over x squared, that's x to the minus second, so it turned into a plus 1 over, well, plus 1 over x. And then a natural log of x plus 1. Right, again, you could u sub x plus 1, but if u is x plus 1, du is just dx. And we just get 1 over u, which is natural log of u, or natural log of x plus 1. You'll see it a lot, you'll get used to it, as long as there's no coefficient, super easy. Worst case, write out the little u sub. And we're evaluating this whole thing from 1 to 2. So we get a 2 plus 2 times the natural log of 2 plus 1/2 plus natural log of 3, right? 2 plus 1 minus, not equals. If we sub in 1, we get a 1 plus 2 times natural log of 1, which will be 0. 1 over 1 is just 1, and then plus the natural log of 2. All right, we can simplify that. We get a 2 plus 1/2, or 5/2 inside this first one. We maybe don't need the parentheses anymore, but a 5/2 plus 2 natural log of 2 plus natural log of 3. And then minus 1, minus 1, minus 2. Minus 2, oh, minus just ln 2. Because again, that 2 ln 1 is just 0, so that term goes away. And then simplifying more, 5/2 minus 2 is just a 1/2. 2 ln 2 minus ln 2 is a single ln 2 plus ln 3. You can either write out as 1/2 plus ln 6, right, multiplying those together, or get some approximate value that I didn't do. All right, a few more. For 5, we need to factor our denominator, so we can take out an x first. We're left with an x squared plus 2x plus 1. That's an x times x plus 1 quantity squared. So we can rewrite and do our decomposition over here on the left. So our original 5x squared plus 20x plus 6 over, we can just write it as x times x plus 1 quantity squared equals a over x plus b over x plus 1 plus c over x plus 1 quantity squared. And if we multiply both sides by the LCD, we end up with a 5x squared plus 20x plus 6 equals a times x plus 1 quantity squared plus a b x plus 1 plus a cx. And then starting with our zeros, if x equals 0, we get a 6 equals just an a there. Right, 0 plus 1 squared would just be 1. The bx and cx terms would lose, would go to 0 if x is 0. And then if x is negative 1, we get a 5 minus 20 plus 6, or a negative 9, is equal to, the a and b terms would go away here with that x plus 1 factor, and we just get a minus c, which would say c is 9. And then we want to find b. So we can try x equals 1 again here. We get a 5 plus 20 plus 6, or 31, equals 1 plus 1 is 2 squared, a 4a, plus for b, we get a 2b, right? 1 times 1 plus 1, or 1 times 2, and then plus c. And filling in what we know, we've got 31 here equals 4 times 6 for a, plus 2b, plus 9 for c. So 31 equals 24 plus 9, or 33, plus 2b, which means negative 2 equals 2b, and negative 1 is b. So we can rewrite our integral after the partial fraction decomp as an a, or 6 over x. B is negative 1, so plus negative 1 over the quantity x plus 1. Plus, for c, we had a 9 over x plus 1 quantity squared dx. First one is just a extra constant factor, but 6 ln x. Second one, we'll get a minus ln quantity x plus 1. And for the last one, we could do that simple u sub again, or you can think of it the same way we did for the ln next to it. It's just a u to the negative second, so we get a negative 9 times 1 over x plus 1 plus c. All right, so again, like I kind of prefaced this section with, most of our work is the algebra, the decomp. Right, the integration, pretty straightforward once we get there. Maybe you got to write out a couple extra little u subs, but they should go pretty well for you. And 6 here is almost prefactored for us. We've got to take an x out of there. I guess I didn't want you to have to break down a big 4th degree polynomial, but you could do some synthetic or some if you had to. But we end up with an x times x minus 1 times this irreducible quadratic, x squared plus 4. So to do our decomp over here, 2x cubed minus 4x minus 8 over x times x minus 1 times x squared plus 4 is going to be equal to a over x plus b over x minus 1 plus, since we've got that quadratic denominator, we need our linear numerator, so cx plus d over x squared plus 4. And then everything else works the same way. We multiply by our LCD to clear out all the denominators, and then get a nice equation to work with, which gives us a 2x cubed minus 4x minus 8 equals a times x minus 1 times x squared plus 4 plus b times x squared plus 4 plus c x plus d times x minus 1. And so if we start the same way we've been doing it, if we take x equals 0, because x is one of our factors, we end up with a negative 8 equals, the b and cx plus d terms will be gone, right? They both have a factor of x in them. And so we're left with just the first one. We get an a times 0 minus 1, negative 1, 0 plus 4 times 4, or negative 8 equals negative 4a, which gives us a equals 2. And then our other 0 would be 1. If we plug in x equals 1, we get a 2 minus 4, negative 2 minus 8, negative 10 equals. The a and cx plus d terms will be gone. They both have the factor of x minus 1. So we're left with just a b times 1 times 5, or 5b. So negative 10 equals 5b. Or b is negative 2. All right, and you could start plugging in some other values, but you'd have to plug in a few to get a system. So here we can talk about the system of equations as well. And so if we want to equate coefficients, so we've got some more algebra to do over here. 2x cubed, I'll put in a 0x squared, so we can equate the quadratic coefficients. Minus 4x minus 8 equals, if we multiply all that stuff out, we get an ax cubed minus ax squared plus 4ax minus 4a, and then plus a bx cubed plus 4bx plus, this will be x squared minus x, cx cubed minus cx squared plus dx squared minus dx. All right, and if we equate coefficients to get our system, 2, right, our cubic would be equal to a plus b plus c. Our 0 for the squared would be equal to negative a minus c plus d. So minus a minus c plus d. And then the negative 4 for our linear, going to be equal to 4a plus 4b minus d. And finally, our constant, the minus 8, would be equal to just the minus 4a there. All right, and the constant one is always going to be what you get when you sub in 0. So that one we already know, a equals 2. You could get it again here. We also have that b is negative 2, so that might come in handy. It looks like that could help us solve for c here. So we get 2 equals, a is 2, plus b, or negative 2, so minus 2. Come on, eraser. Plus c. And that would give us a 2 equals c. If we do add the first two equations together, right, we've got a minus a and c minus c. So if we add these together, we get a 2 equals b plus d. And we already know that b is negative 2. So 2 equals negative 2 plus d, or 4 equals d. So we get for our integral here, keep all that as scratch. All right, that's basically the problem, but that's the scratch. Is equal to, a was 2 over x, plus b was negative 2 over x minus 1, plus we ended up with a c2x plus d over that quantity x squared plus 4. Not 2x plus d, d was 4. 2x plus 4 over our quantity x squared plus 4 dx. All right, and so this will be a common occurrence with the linear numerators when you get two terms. We're going to want to split those into two different integrals. So 2 over x minus 2 over x minus 1 plus, we'll put it as a 2x over x squared plus 4 plus a 4 over x squared plus 4. All right, and there's a lot of room here. The last two we can show some work for, so let's write some scratch right in the middle, and then we'll reconvene at the bottom. But the integral 2 over x dx is just 2 natural log x. The integral minus 2 over x minus 1 dx is a minus 2 ln x minus 1. The integral of 2x over x squared plus 4 is a nice u sub, but we can write it out. U equals x squared plus 4. Du equals 2x dx, right, that whole numerator. So this is just the integral of 1 over u du, or natural log u, which is natural log of x squared plus 4. And the last one's just an arctan. If you practice with them, you'll get used to it. The integration would give us a 1 over a arctan x over a, but we'll do the u sub for it this time. So we can think of it as 4 times the integral of 1 over x squared plus 4 dx. And if you want to make it into the perfect something squared plus 1 for arctan, we've got a factor of 4 out of the denominator as well. So 4 over 4 out front would just be a 1, but we'll write it for a step. We get a 1 over x squared over 4 plus 1, which is going to be a 1 times, so just integral of 1 over x squared over 4 is x over 2 quantity squared plus 1. And then for that, if we take u equals x over 2, du is going to be a 1/2 dx, or 2 du equals dx, gives us our sub. So our integral of 2 times the quantity 1 over u squared plus 1 du. You can see now is that nice arctan. If you've got to do the trig sub that we did in the, I think the classwork for 7.3, you can, but hopefully you're going to memorize those two, arcsine and arctan, that we talked about. And so this one will just become a 2 arctan u, where u is the x over 2, right, that we subbed in. So 2 arctan x over 2. All right, and so the 1/2 arctan x over 2, or 1 over a arctan x over a I was talking about, if we didn't factor that 4 out up here, we would have ended up with a 4 times 1/2, which would have given us the 2 out front. So if you memorize that, it'll come in handy. You'll get some of those tan ones. And so, okay, our whole integral down here, let's see if we can rewrite some stuff. If I've got it somewhere nice, instead of all that along the side. Our integral of 2x cubed minus 4x minus 8 over x squared minus x times quantity x squared plus 4 dx is going to be equal to all those things together. So 2 ln x minus 2 ln x minus 1 plus ln x squared plus 4 plus that last one, 2 arctan x over 2 plus c. All right, so that one a little longer, but it was a lot of stuff involved in that decomposition, and then some u subs that maybe you'll have to write one out, but that arctan one you'll probably get used to. It'll be a nice quick integration at the end as well after you practice. All right, 2 more. There's 2 more cases we can talk about. For this one, we've got the repeated irreducible quadratic. So when we go to our decomposition over here, 8x cubed plus 13x over x squared plus 2 quantity squared would be equal to ax plus b over x squared plus 2 plus cx plus d over x squared plus 2 quantity squared, right, to account for the multiplicity of that irreducible quadratic. And so when we multiply by our LCD, x squared plus 2 quantity squared, we get 8x cubed plus 13x equals ax plus b times quantity x squared plus 2 plus cx plus d. So I already had the whole denominator. All right, and so you could maybe plug some stuff in here to find some zeros, but we'd have to pick some values for x. There aren't any nice convenient zeros, so we can do the equating coefficients part. If we multiply out that right side, we get an ax cubed plus bx squared plus 2ax plus 2b plus cx plus d. And so right away with just the 1 cube, we've got that a equals 8. Because there's no quadratic on the left, we get a 0 equals b. For our linear term, 13 is going to be equal to linear, we've got 2a and c, so 2a plus c. And we already know that a is 8, so we can sub that in. So we've got a 13 equals 16 plus c, or -3 equals c. And no constant for d, so we've got a 0 equals, don't forget the 2b, or tell myself, 2b plus d would be 0. Those are our constants. But we already know that b is 0, so really this is just saying 0 equals d. All right, so b and d are both 0. It's going to make this one nice and easy after that long one we did for 6. And 8's pretty quick too. So our original integral is equal to, for a, we've got an 8x over x squared plus 2. And then for c, we got a -3, so -3x over x squared plus 2 quantity squared dx. All right, and just to make it easy, we can take the coefficients out there, the 8 out front here. Integral x over x squared plus 2 dx, and then a -3 integral x over x squared plus 2 quantity squared dx. And even though one's squared and one's linear, or one's to the first, we can use the same u sub for both. So u equals x squared plus 2, du equals a 2x dx, or because we pulled out those constant factors, du over 2 equals x dx. So the first one we can rewrite as 8 over 2, or a 4, times the integral 1 over u du. And the second one, we're going to get a -3 over 2 times the integral 1 over u squared du. So first one, we get a 4 times the natural log of absolute u, minus a 3/2 times minus 1 over u, and then our plus c, and then subbing in for u. So 4 natural log x squared plus 2 minus 3/2, well, we can put it as a plus 3/2 times 1 over x squared plus 2 plus c. All right, and the last one. Last one, we don't have a nice rational function. At least with algebraic pieces, we've got some transcendental functions, but if we do a u sub, we'll turn it into a partial fraction decomp, so that's why it's here. So we've got sine in the denominator. We know its derivative is cosine, so that's what would make us think maybe some u sub would work. So if u equals sine x, du equals cosine x dx, and we've got our substitutions, so equals here. We've got a 1 over u times the quantity u minus 1 du. That we're going to set up our partial fraction decomp for. So 1 over u times that quantity u minus 1 is going to equal a over u plus b over u minus 1. Multiplying by the LCD, u times u minus 1 leaves us with the equation 1 equals a times u minus 1 plus b times u. If u is 0, we get 1 equals minus a, or -1 equals a. If u equals 1, we get 1 equals b. So we can rewrite our integral one more time as the integral of a was -1, so -1 over u plus 1 over u minus 1 du, which will give us a minus natural log of u plus natural log of u minus 1 plus c, or a minus natural log of u with sine x plus natural log of sine x minus 1 plus c. All right, that's it for 7-4. So lots of partial fraction decomp, lots and lots of algebra, and then hopefully pretty easy integration. But go practice.